Great, so now the recording is going on. Konstantin, the floor is yours. Thank you.
Many thanks, Fernando, and good afternoon to all participants. Also, Happy New Year from me and also from Kema team working on this project, and wish you all the best to you personally, families, and friends. Now we continue today with session number 6, which is called efficiency assessment. People who participated before in this series of webinars, they remembered we discussed different forms of regulation, and one of the form was the so-called incentive regulation, which aims to encourage the efficiency increase by the companies which are regulated. And one of the issues in this incentive regulation is to establish the efficiency increase requirement, which is called also anticipated efficiency increase by the regulator. And this session actually today is devoted to this issue, how we really measure the efficiency increase and how we measure really the efficiency, how we assess the efficiency, and then afterwards how we really integrate the results from this efficiency assessment in the price control process. Now, if we proceed with the agenda, you can see a couple of the first point, a couple of introduction words, what is the role and why we measure efficiency. Then the major part of the session is really how we mathematically, what are the models, mathematical models to assess the efficiency. What you see here is the different names of the models. We explain them shortly during the course. And afterwards, also a couple of words related to the integration of efficiency results. It is again very long topic, which could be really a separate session per se, how really just we integrate the efficiency scores in the price control. We just try to be here condensed, reasonably condensed, and also to explain the major points in the integration process. Now, starting with the first point, why we measure efficiency, I already mentioned that we discussed and explained in the previous session the concept of incentive regulation. For the people who didn't participate, what you see here is really the time on the vertical axis, and in the incentive regulation case, a regulator does not react immediately every year, but just really using a predefined longer than 3, even sometimes up to 5 years regulatory periods. And during this period, the company can really perform better or worse than the regulatory expectations. What we see here, that's really the graph, how a regulator expects or requires the revenue or price will develop. And here in this line, regulator incorporates also anticipated efficiency increase. And just to really define this anticipated efficiency increase, sometimes called X factor, regulator needs to apply efficiency assessment techniques. Sometimes this is also called benchmarking in the literature, just means comparison between the companies to establish the efficiency position or the efficiency score. The purpose of this again is just really to measure the anticipated efficiency increase and also to facilitate, actually to enable the incentive price control. In terms of concept, when you see what is efficiency, you can see different discussions. Sometimes people define efficiency as relative efficiency only. Sometimes the absolute efficiency is called in the literature productivity. What we're using here is just the word efficiency, first as the absolute efficiency level, which it means output divided by input. How efficient is a process, in this case, how efficient is a regulated company. And also what you can see, there is a second term, which is called correction for environment. It is just for the purposes of comparability. Because when we compare the companies, moving from really one concept of relative or absolute efficiency towards really the relative efficiency, it means comparing the companies, we have to have also really adjustment for the operating environment. So it means companies which have not really the same operating environment have to have also kind of, let's say, correct efficiency assessment. So we have to really make them comparable. So now if we formalize the process, for example, in this case is a distribution company, which is the ideal candidate for efficiency assessments in a distribution electricity distribution company, we can really simplify the production process. We say production process, it means that actually the normal microeconomic term does not mean the company is producing electricity. In this case, just production process is called really the process of the functioning of the company. So we're using on one side inputs. So the company, like any other company, has to employ people, have to have also operational costs. Fuel is a small component. It's not really just so strongly relevant for distribution company, but could be also very relevant for production company, like for example, generation business. And on the other side, we have the output factors. In this case, is exactly what is the output of the production process of this company. It could be, for example, customers connected, delivered electricity, the so-called electricity throughput, kilowatt hours, or peak load. So that's how input and output really look like. And then we have also so-called environment. So as I already said, we have to really just introduce additional variables to characterize the operating environment of the company. One company could be small, one could be big. We can also introduce firm size. One can have a really very long network because of rural regions. Some other could be very urban, short network. Some have overhead lines, some more cables. We can have a different climate in case, for example, a very big country with different also really geographical areas. We can have also different topography and terrain. For example, many forests or lakes in some area of the electricity supplies, in some other area not really there. And also that's why we have to really also adjust here. And the task complexity could be also different, as already said, because of the topography, because of the terrain, but also could be for different other reasons. So all these environmental factors have to be introduced also in the model. And in this case, what we can do is we can measure the efficiency of the company. And if we have many companies in the sample, we can go from the concept of absolute efficiency, just one ratio, towards relative efficiency. It means comparing the efficiency position of a company towards other companies and establishing really the relative efficiency, which will be really the effect of, let's say, comparing the two absolute numbers and just establishing who is more and who is less efficient. I mean, there are reasons for efficiency change, which are also widely discussed in the literature, why we have to really repeat sometimes these efforts or this benchmarking. The classical reasons for efficiency change from one to another position is first the technological change, which sometimes is called frontier shift. It means the change in the production technology, the technological progress, introduction of new technologies, and technology development. We can have also the so-called efficiency change, which is the really catching up. So one company can improve its efficiency even without technological change because of changing or better utilization of the existing technologies. And in this case, it could be because the company is just improving the managerial, pure technical efficiency, really just better utilization of the business, of the existing technologies, improvement of the business processes. Could be because also change of the scale of production. So it means company can become bigger or smaller if the previous scale has been not really optimal and not very efficient. Could be also because of changing the allocative efficiency. It means changing the mix of the producing outputs or the used input factors based on, let's say, changing or based on the relative prices of these factors of these produced goods. That could be also reason for change, more, let's say, referred to allocative efficiency here. And also another reason for change is the changing in operating environment. We have already explained before that efficiency could be influenced also from on the input and output side, but also because of the operating environment. Now, discussing about efficiency, we have to really say that one really point of the efficiency is the really measurement per se. It means how we measure the efficiency. The relevance of the efficiency assessment for the price control purposes of course, goes a bit further beyond this actually efficiency assessment, the mathematical modeling. It goes, as already said in the beginning of this lecture, go towards the integration of the established efficiency scores in the price control process. So what you see here is on the left side is the so-called efficiency, really the process of the efficiency assessment and establishment of the efficiency score. And here on the right side of this interface, you see really the process of integration of the established efficiency scores in the price control process. On the left side, the efficiency assessment, the so-called benchmarking, we can see a couple of really major components here. One is the approach, which we'll explain later today in this lecture. So it means which are the major mathematical models and how it really works with them. The second one is really the structure of the sample. So it means the companies which will be selected to participate in the exercise, the sample, the structure of the companies. Number 3 is the model orientation. It means when we say model orientation, first we can use by a given level of output minimization of the inputs. So it means we're looking really what is the possible minimum of production factors inputs which can be used by a company to produce a certain level of output, or we can go for a second, let's say, different model orientation, that's called output maximization, which will be different logic to say what is at given level of input factors, production factors, possible maximum level of output. So that's called the output maximization. Usually in the electricity business, the regulated companies were using input maximization. So it means we're looking for really possible minimum level of the production factors to produce certain given level of output. Data collection and data validation process is a fundamental because if the data quality is not correct, is not adequate, also the results would be not adequate, and also their application in usage in the benchmark, in the price control process, will be really with limited relevance or with limited role. And then if we move here on the right side, just looking on the elements of the integration, the conversion, we can start with the conversion. It means once we have the efficiency score, for example, 70% company which is efficient, how we can really converge, converse, how we can transform this score in the efficiency improvement target, the first block, and then how we can really use this efficiency improvement target in the price control process. Major factors here which play a role at the so-called convergence time. So it means how long it will take to eliminate, or how long it will expect or require the regulator to eliminate the registered inefficiency. 1 year, 3 years, 5 years, or 10 years. And what will be the convergence profile? So do we want to go for kind of, let's say, linear, one-off, not one-off, or kind of non-linear convergence profile in the time? And sometimes we can use also supplementary measures like inefficiency caps or efficiency bands. I'll explain them later at the end of this presentation. And the next point is the integration. It means once we have really established the efficiency score, the first big point is the chargeable basis on which cost block will be this efficiency scores applied. On the operational cost, on the total cost, ideally we have to always connect the chargeable basis, means the cost on which the efficiency scores will apply, with the input of the benchmarking model, ideally. Sometimes in the practice it could be difficult, but ideally this rule has to be followed. If we're just using the operational cost benchmarking, not really the capital cost, what shall we do with the investments, how the capital costs will be included, then how revenue requirements and how will be calculated, and how really regulatory formula will look like. So that's really the points which are relevant for the integration. Why is so actually really benchmarking relevant for practical purposes? Why it is used widely is already explained, because we have to calculate ex ante the anticipated efficiency increase. When we say we, means that in this case the regulator. That's why with the calculation of the efficiency increase or the X factor, the regulator will really ensure ex ante sharing of the anticipated efficiency gains, number one. And what is important to say here also is that X factor is usually not a confirmation, it's just indication, because doesn't matter which of the mathematical models we're using, they always will remain incomplete and limited in their mathematical properties and capabilities. Finally, we have to say also this point that sometimes there is a really full equivalence between X factor and inefficiency or efficiency increase requirement. So it means we have a full equivalence of the effort of the benchmarking and really the definition of the efficiency increase requirement in X factor. In some other models of regulation like building blocks, X factor can have a wider role. So one is really role to incorporate the efficiency increase requirement, but depending how really the revenue requirements are structured and how the regulatory model works, the X factor can have a wider role. So it means also to have a dual function, including also not only efficiency improvement, but also revenue profiling. Now back to the discussion what we introduced the first place, the models. So it means which are the mathematical techniques to measure efficiency. We can distinguish between a couple of, let's say, generic techniques which are used. Probably the first level of classification is to say, first we're using two types of model. One is total and one is partial. Starting with the simple partial models, they usually defined as a performance indicators or the so-called uni-dimensional ratios. So it means we just select input and output variables and combine them, calculating simple ratios for indicative purposes. They're easy to use, easy to calculate. However, these unidimensional ratios don't have a totality. So it means they don't really consider all input and all output factors. So in this case, it is difficult to arrive at the general conclusion of the efficiency position of the investigated company using only partial methods. That's why usually the regulators prefer using total methods. The difference in this case with the partial method is that in the total method case, we're using more than one input and more than one output. So we're using multiple input and multiple outputs. In this case, we can really just consider the completeness of the process, of the whole production process, and investigate and also assess the total efficiency of the company. Now, depending also on the mathematical technique, this model could be the so-called parametric or non-parametric. So in the parametric case, we're just looking for mathematical function using parameters to connect variables. It means to connect the output in the input. And this mathematical function is arrived usually using traditional econometric or statistical analysis. So investigating the plotted data points, input and outputs, and trying to fit, just to arrive at the maximal fit. It means to find the best really representation of this population of points. And the people remember probably from the statistical courses of statistical books that the traditional technique is called also ordinary least square. I'll explain this later. And also for the purposes of the benchmarking, we can also use the so-called corrected ordinary least square just to move from the so-called average really investigation to frontier analysis. So in this case, just moving towards the best practice in the sample and trying just to tighten the efficiency increase requirements. The last technique called stochastic frontier is again econometric technique, but differently from the deterministic technique here, ordinary corrected ordinary least square. The stochastic frontier also includes stochastic properties. It means just trying to introduce also measurement of stochastic errors and splitting of the efficiency for really technical reasons and efficiency, or in this case more inefficiency because of stochastic error. So all this group, as already explained, is called econometric models using parameters. And the second very popular group, even more popular than econometric models, called non-parametric models, because they don't use from mathematical function, but rely more on the linear programming, the optimization techniques. And the most popular technique is called data envelopment analysis. We'll come to this technique also in a minute. We have also third group, which is called engineering models. In this case, the benchmarking is usually made on the basis of comparison with a virtual company. And in this case, if, for example, we investigate a network, electricity network, the virtual company will be really a fictive, ideal electricity network, which will be created based on the engineering model. In this case, the comparison will be not based with the really actual companies in the sample, but we'll just establish a virtual comparator using this engineering network model. And the efficiency of the investigated, or each of the investigated companies, will be measured towards this virtual company or virtual network. And then we have the final group, which is called index methods. The total factor productivity is well-known established method for this index. In this case, we usually investigated the productivity development. When we say productivity, it means the total factor. So it means using all inputs and all outputs of a company or sector. In this case, could be also sector productivity development. And we are just registering a specific time, for example, annually, the points of productivity level, the absolute productivity, the absolute efficiency, and just trying in the time to compare these absolute efficiency levels and to establish a trend of productivity change. So this productivity change actually is really a criteria or indication for productivity increase or respectively decrease in terms of time. As you see, actually, we have a multiple or several techniques which can be used, and it's not only theoretical analysis, also in the practice, in the daily regulation, you can see that regulatory authorities use different techniques in different forms. And as already said in the on the previous slides, we can distinguish between frontier and average performance in the sample, or frontier average technique, depending whether we want to compare the investigated company with the best performer in the sample or with the average performer in the sample. Obviously, and also logically, regulatory authorities prefer frontier techniques because they set stronger and higher requirements towards the regulated companies. In this case, the company which is investigated, the inefficient company, will be always compared with the best companies in the sample, and logically, the expected efficiency increase will be higher. And in terms of techniques, what we can see really from the practical regulation is that two techniques dominate. One is really the data envelopment analysis, which is widely used in almost all regimes with incentive regulation. And one is also econometric technique, and we see also some in the last years also some trials to use not the classical deterministic economic regression, but also to use stochastic frontier. In terms of really countries where these techniques are used, the data envelopment analysis, we can see application in Norway, you can see the Netherlands, we can see recently in Germany also. Several countries, Central Eastern Europe, have used this technique to establish efficiency for regulatory purposes. And also in terms of parametric economic models, we can see, we've seen also application of stochastic frontier recently in Germany in combination with data envelopment analysis, as already said, but also we have seen even also years, decades ago, in UK application of regression, classical regression analysis for the controllable operational cost for distribution, price control for electricity distribution in UK. Finally, also reference network models have been used more for indicative purposes than really for just to estimate the efficiency and to really base the conclusions for efficiency increase of the regulator on these models, as well as just more to support really than to confirm the efficiency. And we have also two prominent cases in Europe, this Spain and Sweden have been using actually these models, reference network models, for regulatory purposes. Also, we see international applications from South America for their regulatory regimes. Well known is Chile, but also Argentina have done some trials in application also for an application of reference network models. What is actually the result of the efficiency assessment is the so-called efficiency score, as already explained in the previous slides. For example, in this case, we have 5 companies, and one of them, let's say C, is the best one. It is a so-called best performer. It is on the frontier of the efficiency assessment models, so it has 100% efficiency. Companies like A, B, C, D, sorry, and E in this sample have less than 100%. In this case, these companies are relatively inefficient compared to company C. So their absolute efficiency is less than the absolute efficiency of company C. So they are relatively inefficient, and the difference of the efficiency position of company D towards this in C is called inefficiency. Now, this inefficiency has to be converted, has to be transformed in efficiency increase, which is defined by the regulator. So as already explained in the beginning of this lecture, exactly this transformation, this conversion process is also a very important element. For example, in this case, if the company D has 60 or 70% efficiency and 30 or 40 inefficiency, this 30-40% has to be converted, so we have to define an annual efficiency increase target. So we'll come back to this point later in the presentation. Starting with again, back to the efficiency measurement techniques. We mentioned at the beginning of the discussion on the slide with the really classification of techniques, performance indicators, also called unidimensional ratios. What you see here is a number of them. For example, we can combine gigawatt hours, the electricity distributed, divided by number of employees, could be OPEX by gigawatt hours, OPEX per employee, gigawatt hours per line length. So we can have a different, as already said, indicators, and as explained, they are simple to calculate, easy to establish. The big disadvantage that they are unidimensional, they characterize only part of the business production process of the company and not really the whole completeness of this process. That's why they can be really used to support the regulatory work, but really not to lead and dominate the efficiency assessment process. Total factor productivity, I already indicated that actually it is a ratio. First, the absolute productivity will be really a ratio which is defined at a specific time point using the total output. It means the weighted output or the weighted combined output using all possible outputs. Sorry, it's in the denominator. And also the weighted inputs. So it means it will be a sum of the 80 inputs. And in this case, we have to use weighting coefficients. Usually we're using revenue shares for the output, and also we're using usually cost shares for the input. In this case, we can establish a ratio, so it means a number, for example, every year for specific investigated company, for specific investigated sector, for example, electricity networks or energy business, but also for the total economy, if we need that. So when we have couple of numbers, for example, every year, so enough or sufficiently long time series, so series of numbers over time, we can also measure really the trends, and depending how robust is the data and how long the time series are, we can really arrive and kind of statistically significant trends of total productivity improvement over time. This could be used automatically then also for example, for the future. So it means this number can be extrapolated if the conditions for the future are probably comparable with this from the past. One of the big disadvantages in this definition of the total factor productivity is that it's actually a model which is really averaging the productivity or efficiency improvement over time. We don't see the catch-up effect explicitly. However, we have to say also at this point that total factor productivity could be calculated using different indexes. In this case, what you see on the slide is more comparable with the so-called Turnquist index. And also we can have an application of the so-called Malmquist index, which is different type. And this is an index which also measures total factor productivity, but can really disaggregate, decompose, and distinguish between efficiency, which is relative one, and also the catch-up. Frontier methods, as was said before, these are the methods which measure the efficiency position of a company towards the best performer in the sample. And as already said, these methods are preferred by the regulators because they will expose the companies to more demanding efficiency increase requirement. And also we said that some techniques like DEAR, and also, for example, corrected ordinary least square, but also stochastic frontier, they support also these frontier models because these techniques can establish what is the efficiency position of the investigated company compared also to the best performer in the sample. Now we're starting shortly with the data envelopment analysis. What you can see here is a simplified process. On left side, the so-called output-oriented model. It means we are maximizing a production process with two outputs and one input. What you can see here is a population of data points which are connected with lines, and this resembles, if you remember from production theory, the so-called production possibility frontier. It means the possible area of production of two outputs at a level of fixed input. So in this case, if we just we approximate here with this line starting from A to E, which is actually combination of linear small lines, we approximate the production possibility frontier. The question which actually is for us now, if we have a company F which has this location in the graph, what will be the possible improvement of efficiency of the company, it means output maximization, to achieve this fictive, in this case, production possibility frontier. So it means if we are here, and it is possible, if the company is incomparable in the sample, from F to move to the production possibility frontier. So in this case, the point F prime will be the so-called peer company, so it will be really the place where the company F could be. So it means it will be the efficiency improvement. What we can say with simple words is that company F can produce more output from output 1 and output 2 just to arrive at the point F1. And this actually really stretch, or this distance F1 is the so-called inefficiency. It is the minimal distance from F to the production possibility, to effective production possibility frontier, in this case to be really to the line BC. So because F prime will be a combination of the coordinates of point B and C, so it will be a fictive company or fictive point which will be created by linear combination of the coordinates of points B and C. In this case, we have also constraint in the linear optimization process. Company F can move to F prime, but shall stay on the left side of this frontier A, B, C, D, E. So we cannot move on the right side. Again, the definition is really find the minimum expansion from F to F1, but don't move on the right side of the frontier. Similarly, which actually is really more popular, even this model, the so-called input minimization model on the right side. In this case, what we're trying to do is really to minimize the distance F1 again, but the logic is different. At certain level of output, we want to minimize really the input factor commitment. So in this case, again, we're using minimization F1 should be minimal. The same logic, radial shrinkage of the vector F towards the origin of the coordinate system. However, the logic is at certain level of outputs, we have to really minimize or really reduce the inputs which are used. In this case, what we say, company F can go to F prime, the same logic like in the previous case. F prime is the inefficiency. And what should not happen is that really company F move on the left side of the convex frontier. That's so this convexity constraint must really hold. So company must stay on the right side of the frontier line, which is defined by A, B, C, D, and T. In both cases, as already said, using output maximization, input minimization, we just try to establish the efficiency and the inefficiency in this case. The inefficiency in both cases is defined by the minimum extension or minimum shrinkage of the vector starting from origin to F. Again here, F to the origin. And this F prime is the so-called percentage inefficiency, which will really determine the efficiency score or the inefficiency score from the efficiency assessment. One point of DIA, which actually is very interesting, is using the so-called return to scale. So it means that there is possible and is able to discriminate, to distinguish between the efficiency driven by scale reasons, it means the size of the company, or pure technical efficiency or inefficiency. Just, I have to here apologize, the F prime should be really here. So it means the line F prime must be parallel to the horizontal axis. So it a bit happened when we just draw the line, probably it went too high here. So again, F prime should be really parallel here to the horizontal axis. What is important is that we can distinguish between the so-called constant return to scale. It means proportional change of input will lead to proportional change of output. It is the line which is defined between the origin of the coordinate system and point A. That is the line which is characterized really by linear production process, constant return to scale. So input will increase 2 times, output also. Input will decrease with probably 2 times, output also. We have a complete linear relationship, proportionality. But also can have also different characteristics. We can have also non-proportional really relationship between input and output. And in this case, for example, in the area CA, we'll have different non-proportional change. For example, if the input increase, one time the output increase stronger. So we have an area of increasing in terms to scale. Differently in the area AB, so we can have the so-called decreasing in terms to scale. So in this case, input increase of 2 times will lead to increase of output less than 2 times. So area CA, actually the whole area here, CA, and area AB, an area which are not characterized by non-constant return to scale. And also you can sometimes see in the literature the word variable return to scale. So you can see in this graph that it matters when we really measure the efficiency towards the line O, the origin, begin of origin here, the origin of the coordinate system, OA, O if the frontier is defined as a CAB. So company will be less inefficient if we define the frontier by this line. So it means variable return to scale will be more generous to the companies. What does it mean in practice? If the regulator is using variable returns to scale, it means that the regulator really admits that the size of the company, the scale of production, is not completely controllable. So if the regulator believes that the scale is completely controllable, in this case they can say, yes, we'll be using constant return to scale, because the company can control the scale. So if they're not at the optimum level, so for example, if they're here or here, they can really move up or move down, just change the scale and arrive at the optimal level. However, if the regulator does not believe that it's possible, at least in short term, in this case, the regulator can use variable return to scale and relax the frontier lines. It means becomes more generous to the companies and also reduce the anticipated efficiency increase. We have already explained there, that's actually the major properties in a nutshell, what you see on the slide 15. Important is that actually is really non-parametric technique. We don't see a mathematical really function between input and outputs, and the peer companies which is established via linear optimization, solving linear equations and finding the optimal weights in this actually solution of the linear optimization problem. When we say about advantages, discuss about advantages and disadvantages, what is really important to say is that we can see peer companies with data, so it means we can see which is really how the comparator has been established. That's really one of the biggest advantages. And also what is very important also, as explained in the previous slide, is that we can distinguish explicitly the scale from non-scale efficiency or inefficiency. So we can see really exactly what is the pure technical efficiency, inefficiency, and what is really the scale-driven efficiency or inefficiency. In addition, also, we can distinguish between allocative and technical efficiency if we have sufficient information. The disadvantages of data actually is well known, that actually it could be driven, the model can be really driven by really extreme data or inadequate data. So we can have a data mistake, and of course, because of the model, we can also really arrive at really not incorrect or non-adequate results. One additional point is also that the data is sensitive to the number of input and output. If the sample is not really large enough, we can have the so-called specialization problem. So all the companies which have extreme characteristic in one or other area of the output definition can become or can appear efficient in the this benchmarking exercise. Last but not least, also sometimes, as already said, because of the properties of the models, we cannot really control explicitly, automatically in the model for statistical significance of the result. And if you see now the econometric approaches, we have explained before also what is really the difference. These are parametric models. That's why differently from there, in contrast to there, they're using explicit mathematical function. And as already said, the O's, ordinary least square, this model really will determine the optimal fit. It means the line here using the ordinary least square. So it means what we're trying to do is to minimize the sum of the square distances of these points, the plotted points, and the line which we are searching for, the optimal fit. So we can say that this line will be the best characterization of the population of these here plotted points. And if we move this line, the so-called O's line, ordinary least square, towards the biggest residual down in the graph, we'll arrive at the corrected O's. So it means the so-called cos, corrected ordinary least square. So this line, the new line, is really the best frontier, the best practice line. So it means it's the frontier line because it is really characterize the efficiency position of this yellow point, which is the best performer in the sample. Now, if we measure efficiency of all this observation towards this line, so we can see, of course, the relative inefficiency of the investigated companies towards the best performer. And now, if we discuss or decide to use stochastic frontier, what we see here is again additional correction of the deterministic line. Corrected O's is a deterministic line. So we ignore in this case any stochastic noise, stochastic errors. So we can really adjust this corrected ordinary least square towards a new line. Even though it will be not a line, it will be probably something like a snake here. New population of points, which is called stochastic frontier analysis. In this case, we'll really use we'll consider explicitly a splitting between the inefficiency and the stochastic error. So it means we'll relax a bit also the efficiency frontier because we'll clean up the results from possible stochastic errors in terms of measurements or non-systematic effects. So that's what you see here is really, again, short description of the models. We discussed this one, and probably we have to, we'll move to the next part of the presentation. Shortly, probably to say something again on the Coles model, on the deterministic regression using corrected ordinary least square. Like O's, it is really important that they have a positive advantage or advantage, a positive property that they can use statistical, or they can also measure statistical significance in the sample. Probably one of the serious problem with them is first really the point that they don't measure stochastic error, and also second, also it's like any usually normal econometric exercise, they will require large data volume and also robust regression relationship just to create a robust regression relationship. And as you seen probably in the graph before, because we're moving towards the biggest residual to establish really the cost frontier line, so it means if we have outliers, it means if the data is not well validated or is not really with significant adequate quality, in this case we can really arrive at incorrect and also unrealistic frontier line, and in this case of course very unrealistic results. So it means we have to be extremely careful with the data quality. We have to apply the cost technique. The same is for stochastic frontier. Positive here in the stochastic frontier case that we can really isolate stochastic noise. It means we can adjust for stochastic errors. Again, like the previous case, we need significant volume of data, large data sample, and just to arrive at this, let's say, robust results, plus also the stochastic frontier case, especially this method is mathematically very sophisticated, and also in many cases it creates black box effect and is lacking transparency. Finally, as already explained, we have the virtual network models. Differently from the other models, we don't compare automatically company with company, so we don't have a comparison company with a company in this case, but we compare the investigated company with a virtual network. So in this case, network which is established, created by a specific computer model based on engineering principles. So we just really, based on the operating environment and specific, for example, case, we really establish a virtual network. So we construct a new network, and also we establish the revenue allowed, the efficient revenue based on this new configuration. And as already explained before, in this case, it's a good technique. However, the application is always indicative, because I mean it is very difficult to approximate the actual operating environment. So we have cases only in Spain, and in Sweden, in Europe, also in Germany was experimented a bit with the network model. So far we don't have really results, or no application for the benchmarking purposes automatically. But again, these trials have been, all these countries have been indicative just to support the efficiency assessment process and not to determine and to dominate this process. Shortly also on the really application of the results, what is fundamental actually is not only the efficiency score, but also how we apply that. And I said also in the beginning that it could be based also on the total cost, but could be also based on the operating cost. And ideally, so what we're using is the input in the model. For example, if we're using operating cost, that will be really the chargeable volume. So it means we have to apply the efficiency scores on the operating cost. And the classical case of this application is a so-called building block model. So it means in this case, in most specification of the building blocks, we're using the efficiency analysis, the efficiency assessment mainly on the OPEX side, on the controllable OPEX side, and it means the CAPEX, the capital expenditures, are separately investigated and not incorporated in a formal benchmarking model. That's in contrast to a so-called TOTEX approach, total cost. Sometimes people say total cost, but it doesn't mean that actually total cost is different from, I mean, it doesn't mean that actually in the building blocks case, we don't use total cost to allow for the revenue. In this case, total cost refers just for benchmarking, because total cost means that we're using efficiency analysis on the total controllable cost. So it means we incorporate also the capital cost components. Probably that's the big difference between the two models. In one case, the building blocks, we're using mainly, usually, the efficiency analysis on the controllable operating cost. In the TOTEX approach case, we're using the efficiency analysis on the total controllable case. Yeah, we have to say that in both approaches, regulator will allow revenue based on total cost. What is the difference is that the efficiency analysis in the total cost case is just based on the capex and opex together. Capital expenditures are integrated, and in the building block not. You can see different applications in Europe of this building blocks and total cost approach, mainly in UK, but also Central Eastern Europe. And total cost, we have it in Germany, Norway, the Netherlands, Austria. So that's the countries which have started, for example, first Norway 97, but also recently 2009, this year for the first time, Germany moved to incentive regulation, also using total cost approach. What is interesting that some total cost sometimes is supported not only by total cost analysis or benchmarking analysis, but also a supplementary scheme like inefficiency caps. I'll say something about this one in the next minutes. Convergence towards efficiency frontier. You remember we said we have the efficiency scores, now we have to move to efficiency frontier. And also it's a decision of the regulator to decide for how long this inefficiency will really remain with the companies and how intensive, how really fast the extraction of the inefficiency should really take place. What you can see here is actually two trajectories. One is really one path which is one-off and then slower, or just one really proportional every year towards the end of the regulatory period. So you can see also advantages of initial one-off cuts. It means quick or faster inefficiency reduction, so that in this case the efficiencies are very quickly eliminated. On the other side, we can argue that, for example, yeah, it is good to have one-off adjustment quickly. However, it actually that decreases also incentives for the future of the companies to reduce, to improve their efficiency, because we have eliminated inefficiencies very quickly. It is also another point, sometimes very practically discussed, is whether it is possible quickly to eliminate inefficiency, or is it really realistic? Is it feasible for the companies to go for very fast efficiency increase and inefficiency reduction? And finally, the supporting schemes. We said also before that efficiency will result in efficiency assessment will result in efficiency scores. For example, 60, 70, 80%. Some regulators really have decided to introduce supporting schemes. Usually these are hedges as a special really supporting measures to, let's say, counteract to the incompleteness, to the inherent incompleteness of the benchmarking models. So in this case, it's very traditional approach, the so-called inefficiency caps. It has been used in Austria, Germany, but also previously in Norway. What is done in this case is that the regulator defines a minimum efficiency score. For example, in Germany, in the price control starting 2009, it was actually defined 60% for electricity distribution. It means that even the company has less than 60% efficiency score coming from the benchmarking, the efficiency score which will be used by the regulator will be 60%. So in this case, we limit automatically the required efficiency increase. So it means the annual X factor, because the regulator will be using also always this minimum efficiency score of 60%. Similarly, also in Austria, the regulator has defined the individual maximum the individual maximum efficiency increase, exactly, which was what was defined as a set at 5.45%. In this case, again, the logic was similar, that the company will be not required to increase the efficiency more this for 5.45% per year. Another supplementary scheme is the so-called sliding scale, and the third one is the so-called efficiency bands. The last one actually is a simple grouping of the companies with similar efficiency in one efficiency zone, and defining an efficiency band and defining one efficiency increase target for this group of companies of this efficiency band. And another one is the so-called sliding scale. We explained the sliding scale approach in one of the previous lectures. Again, just for people who probably didn't participate, it is a limit actually on the profit in this case, how it's applied in Norway, and it is the method defines a dead band in which the profit can move up and down, and the method defines also these limits, colors and caps actually. In this case, if the profit moves more than this limit, for example 15%, in this case a regulator will look for clawbacks, so the company must really reduce the tariffs. And also if the profits will move or will go down less than 2%, in this case regulator again will allow increase of the tariff. So this is a kind of supplementary scheme which was used in Norway in 1997-2001, the first price control period, and also in 2002-2006, the second price control period, just really to limit the risk exposure of the companies because of the regulation, and to really avoid any significant either, for example, issues on the financial viability if the profit has been really very low, but also to ensure, also to avoid excessive profit. And that means also consumer discussions, also political debates if the profit has been really high. Moving to the summary again, just to summarize the presentation from today, benchmarking or efficiency assessment is very important, especially in the context of the incentive regulation. Incentive regulation requires anticipated efficiency increase by the regulator. Regulator has to use techniques and models to establish the efficiency positions, to calculate the efficiency scores, and to derive efficiency increase factors for the regulated companies. Benchmarking is traditional technique, a set of techniques used to establish the efficiency position, to assess the efficiency position of the companies. We have different mathematical techniques, starting with the econometric, going through the non-parametric models, using also index techniques, and also engineering network approach, but sometimes also unidimensional ratios to support the benchmarking analysis. We have to be also realistic in the application and usage of the results. Benchmarking is just an indication, it's not a confirmation, because of the inherent incompleteness of mathematical properties of the models. And also then it is very important how the results of the benchmarking will be used. It is actually exactly so important like the benchmarking itself, and the regulator has to apply, it has to use the results also in the context of the whole logic of the price control, but also stay realistic in the application.
So
and also
now we have some
trying
few minutes
to achieve
for
robust and
questions.
also useful
So,
outcome.
You
Many
can
thanks
send your questions
for
to
your attention. I'll be happy to now respond to
the
questions.
Q&A window. We can start now. So, Konstantin, I think you can see the list of questions, so you can select those that are applicable and go ahead. Thank you. Yes. Yeah, you can read it, and then I can submit.
Just see you. Probably I see here. Okay. Say the inefficiency can. This one. I see here one question. Yeah. Okay. I see of Michael a question. Hirox, I think you say the inefficiency can be measured on horizontal line. Why not on vertical? Yeah, it is possible. I mean, that's it's a matter of representation. What you see on the graphs is really just simple representation. In the case of one input and one output, it is absolutely conventional when you want to put the input and output. What is important is how your model works. In case of one input and output, and just for example, if you're using output maximization model, it means you're looking for a fixed level of input, maximum output. If you're using an input minimization model, you're looking at the fixed level of output, minimum level of input. If you have multi-dimensional, more than 2-dimension, for example, 3 or more than 3-dimensional models, it's difficult to represent them. However, we done actually a trial. If you see also our slides, when we discussing DEAR,
Thank you very much.
so we have
Constantine.
actually 2 inputs
So
or 2
we have,
outputs. So it means we have 3-dimensional model, because if you have 2 inputs, you have also one additional output. You have 3 dimensions. What you see is just really a simple plot on the input factors. You don't see really the third dimension where the output should be represented. So it's a convention. Yeah. There's many questions here. We just have to, first one, could you please elaborate on the perceived efficiency of different countries within Europe in terms of electricity production? Again, what you see, the whole public literature and what is used actually is publicly available, and a lot of discussion is on the regulated areas. So it means in Europe especially, you see probably a lot of analysis carried out by different regulators and different consultants on the electricity networks, more for distribution than for transmission. And I doubt whether you see anything on the electricity production, if you mean here really generation in this case. Generation is deregulated, and also it's not subject to any really discussion about efficiency of the regulator. You can see work on the generation electricity markets, which is more in the area where the competition can work. But it's a bit different from ex-ante regulation. And what I explained today is usually this case, efficiency analysis usually is done for the really anticipated efficiency increase for the ex-ante regulation purposes. That's one very important point. So in this case, I doubt whether I'm very skeptical whether you see something on the European level about really electricity production inefficiency. Yeah? For electricity networks, yes, you will see a lot of information. You can see many things done usually by national regulators. You can see also international work. For example, recently was the last year was done something on electricity transmission, which was international work comparing also international analysis, different national transmission system operators. And also results have been done, and I think even disclosed by the German regulator. It was actually really leading the effort, but it was a cooperative effort by many countries from European Union. That's why is there, the second part of the question, is there any European Union-wide study on efficiencies by operators? Yes, there is. I mean, this, for example, this one. And sometimes you can see also in, for example, European ERA, that's called the Energy Regional Regulatory Association. It's more centralized in European countries. They just try to do also something on the inter-regional or supranational level. In this case, it will be outside of European Union a bit, because they compare companies or countries, companies in the countries which are outside of some of them are outside of the European Union. I've never seen one really study, for example, for distribution companies or other related companies, which is for the complete European Union and just to establish the efficiency frontier for the European Union. What I've seen, as already said, is really the last year, the study of the European Union regulators on the transmission system operators. However, I have to say here that it was a lot of plus and minus views whether this study is really, really strong and strong enough actually, and is it possible really to go for such study when you have so many complexities, especially in the transmission area business. Good. The last point is actually again a question. Germany is noted for having high electricity prices in poorly functioning markets. Is it efficiency regulation to blame at all? I'll split here the question because if you see that there is a very high electricity price, we at least in simple terms we can split the question in two. Something it does not work on the generation side and the supply side. It means the electricity market and in the regulated areas. In this case, for example, electricity networks. If there is actually inefficiency coming via the electricity networks, of course you can say that regulation is here responsible for that. That was the reason actually for in Germany to introduce incentive regulation. And from 2006, we explained in the previous lectures, to 2008, regulator has done a lot of, 2009, actually 2008 till the end of 2008, regulator has done a lot of really work just to try to introduce a concept which really will aim mainly to increase the efficiency.
Okay, very well,
Constantine,
thank you very much.
That was the purpose. It means,
I see that there are some requests coming from Nigeria
that there is
to
an
get
inefficiency in the electricity networks,
support
and the regulators should do something.
KIMA
And that was really the work,
assessing
as already said, to
their
design and implement the incentive regulation
So
2002,
for any
2006,
particular
2008.
request, as I
Inefficiencies on the
indicate
generation
here,
side,
you can
electricity market
submit
is
your
something different. It's
requests
not really for this
to
session.
Konstantin Petrov at this email address. Beyond that, Konstantin, if you have some additional comments on whether a KIMA is present in Africa or willing to provide physical training or whatever, thank you.
Right. I mean, just yeah, we've done work from Africa. It's not probably not the proper timing just to say now what we for this project, but we've done actually work in Africa. We'll be doing also this year some training activities we have also in this region, specifically in Tanzania for many countries. So actually, that's also part of the markets of KEMA.
Great. So
otherwise,
thank you very
apart from
much,
this
everybody.
story with this announcement for
Konstantin,
Africa,
I don't know
just
whether
want to
you
say
have
many thanks for your participation in the session.
for the
And
last
as
question
usual,
coming
as
from
Fernando
our
knows,
audience.
we will
Thank you.
be happy to respond 5 questions in written way.
Okay.
And just look forward to the next session, which will be for quality of supply regulation.
Yes,
Many
it's
thanks,
about.
and
I'm sending.
have a nice day. Bye.
To the Q&A chat. So what can you say us about the homogeneity of firms to be compared, particular electricity distributors, as they are quite. Thank you.
Yeah, I'm here. Which is this one, Fernando? Yeah, I see. Yeah, that's yeah, it's a very good question. Actually, it's a really fundamental point. Even if you have a national comparison, for example, let's assume that we have a big sample, like for example the case in Germany, when we have many companies, national distribution companies to compare. That was the case in Austria. That was the case also in Norway. So they have we have big sample, but the question is very nice because even in this case the companies could be really different. So what is usually done, actually, you have a couple of approaches. One is to really fragment the sample, to say, okay, I'll establish really subsamples, the companies which have different characteristics, just to make them homogeneous and comparable in subsamples. That's one approach. Actually, it was not used in Germany. It was in Germany, they said we want to have, it was not also used, I think, in Austria in this way completely. The idea was really to establish or to measure the efficiency in one big sample, but to introduce several environmental factors. And that's really the point. And if you go to our first slide, when we start really explaining the efficiency concept, we don't have only input and outputs, but we have also really environmental factors. So it means exactly these environmental factors, they measure really, or they characterize the operating environments. And the question actually is, if you have different companies, for example, if one company operates in the city, one in the rural regions, if
okay,
one
great.
company has
thank you very much,
cables,
Konstantin. Now, yes, we can
if
adjourn the session. So thank you very much,
Konstantin.
It is thank you very much, the
with
audience.
The model specification and
this
also
was
with the model
6
orientation
out of 8
and the selection of technique that
about
we take roughly, not everything perfect, but also roughly and also reasonably well.
So here you are
really
the link
criteria. So it
for
means
this session,
to make
but
the company
on the
in
same
the
email
mathematical
address you will
exercise
find the
comparable.
links for the previous ones. So thank you very much and see you in 15 days in the next session. Goodbye.